All right. Hello, everyone. So I see some of you are already here, and thank you so much for coming. So I will be kicking off this session then. Um, Again, thank you for coming. So today I'm talking about MLOps. It's just HPC in disguise. This is a quote from my CEO and colleague. It's really, really interesting. So I'll be talking about what that means. And also, it's a no-nonsense guide to a better workflow. And with no-nonsense, I mean, or I try to mean, that I won't be using a lot of marketing terms. I won't be showing you a lot of different features or, oh, wow, look at what we can do, what this can do. It's essentially just like showing you a workflow, showing you how you can go from training a model all the way to serving it as well, hopefully in a very interesting manner, and hopefully teaching you some things along the way. We'll also have a really cool demo about introducing drift in the model to try and monitor it, right, so that you can see it happening. And of course, it's still ClearML. There should also be some memes at least. So again, thank you for coming, and let's get started. So first of all, who am I? Who is the person you're listening to? So it is, I'm Victor Song. I'm a developer advocate at ClearML, and I've been working in the ML engineering sphere for 4 years. So I'm not exactly super old, but I have some experience at the very least, more than enough to know the very annoying things data scientists and ML engineers have to go through on a daily basis, right? So this is the kind of talk that tries to address those things and offer you some tools that can help you there. I'm also working on YouTube videos, most of the time on the ClearML channel, but also others, and also blog posts. But I also love tinkering and making things with ML, with machine learning. For example, you will find the ML Maker channel on YouTube that actually made a PC lock screen that only unlocks when you do 5 push-ups, which are detected obviously by machine learning. So if you like things like that, that could also be interesting to look at. Right, so this is who I am, but enough about me. So first of all, let's tackle the title, right? So HPC in disguise. I don't necessarily I don't necessarily have a background in HPC, but from what I understand, it's multiple users running tons of parallel workloads on lots of remote machines. Essentially, like a layman's terms, that is what it is. And my CEO had this insight that essentially that's what machine learning is trying to do, right? We're also running tons of parallel workloads, which are training runs on lots of different machines. And we have kind of the same challenges, which is why the tools that are being built right now for MLOps actually are relatively similar to some of the tools that are already out there for HPC. And it could be very interesting to take a look at that. So for example, remote execution of packaged reproducible code is something that we, as ML engineers, struggle with a lot as well. Also multi-machine and cluster orchestration. So if you want to do remote machines or remote machine execution, but also multiple machines, orchestrating them together into a cluster so that you can just throw things at it. That's also very, very interesting. You also have multi-user management with queues and priorities. So especially here, queues and priorities are something that is very well known in the HPC sphere. And well, essentially, it's a very useful thing in MLOps as well, because you have those same kind of hard, heavy workloads that take a long time, and you want to be able to efficiently schedule them on your given machines. And then, of course, there's monitoring machines and workloads. If anything goes wrong, you should know why. If anything goes well, you should also want to know everything that happened there so that you don't actually lose any of the content of what you're actually trying to do. And obviously lots more. So MLOps is essentially doing the same thing. That's what I'm here to try and tell you. But mainly we're going to talk about a workflow using these kind of tools that have a parallel in HPC. So the use case, right? This is going to be the thing that we're talking about for the next hour. So I won't bother you with slides too much. I have some just to give an overview, but I'll be diving into the code and into the terminal and whatnot very, very soon. So just so that we have something to talk about, let me introduce the relatively simple machine learning use case that I prepared, but it might hopefully be interesting and just show, the focus is still on the tooling, right? So the machine learning is not super complex, but the tooling is what takes the cake here. So what should receive the most attention. So what we're going to do is asteroid detection, right? This really cool data set from NASA with a bunch of different asteroids, and you can detect based on their features whether or not it's going to be hazardous or not for Earth, right? So that's a structured data example. There's obviously many more that you can have, but this was an interesting one. And so you have features like absolute magnitude, which is like the size of the asteroid, estimated diameter in kilometers, which is obviously diameter, and so on and so on. So all describing features of those asteroids, and every single row in this sample or in this data frame essentially is an asteroid, right? And what we're going to want to do is first dissect it, right? And then pre-process it and then train a model on that so that it can detect or that it can give you the if it's hazardous or not based on incoming new samples with these same features, right? And then we're also going to serve that using ClearML serving just to give you an idea on how easy it can be just to take a model and then serve it outright. For those of you who want to follow along, it's pretty hard to do this live with only myself, but you can always follow along and use this video or like the recording of this video as a guide. This is where the actual code that we're going to use today is located. It will be moved to the ClearML examples shortly, but right now it's on this link. This link will stay for a few slides. So if you're interested or you're there with your laptop, why not follow along? It could be interesting. Right. So what will we be building, right? The workflow that I was talking about. Essentially, what I'm hoping I can get with this talk, or I can teach with this talk, is just to give a few tools that you might have already used, that you might already heard of, or that you might not use at all yet, and just show you how you can combine all of these tools and all of these ideas just to get a complete workflow from beginning to end, right? And hopefully you pick something up along the way. So this is structured. You might not see it. We'll zoom into each block specifically later on, but you might not see it. But in the it's actually split into three phases, right? Excuse me. The experiment phase, the productionizing phase, and the deployment phase. So the experiment phase is where we'll start earlier on. It's essentially what a data scientist does on a daily basis, right? We will take the use case, try to create a model, iterate a little bit, and then we will go into the productionizing phase, which will automate a lot of this experimentation, because at some point it stops being useful or efficient to go or to keep working in like notebooks or like small scripts or whatever, and just to automate everything that you have, just changing parameters, right? If the code structure, the base is good, you can just change parameters and find the best combinations there. Also, we will be seeing how to run all of this code on remote machines as well, which is always interesting to see how that works, because yeah, like I said, it's HPC, right? These remote machines, the tools to use them, they're very similar, and it's very useful to know them, I think. And then there is obviously the deployment phase that I was talking about before. So essentially, we're going to set up a serving engine, a model serving engine for the model that we just trained, right? In the productionizing phase that is based on the experiment phase. And then we'll also set up some model monitoring that will then catch a demo that I will give for where we actually generate some drifted data, right? And then hopefully we will be able to flag it. And then if you follow along and you know this whole pipeline back to front, then it means that we can very quickly start to iterate and change things way earlier in the pipeline, and then just redeploy the model very, very quickly. So that's actually a nice boon or a nice bonus that you get from using these tools well and having your workflow click into each other very, very well, like just like a puzzle, right? So again, the GitHub for that is here. So let's start in the first phase, right? The experiment phase. So what can you see here? There's essentially 3 Python files. I'll go on them in the code editor really quickly, but essentially there's 3 stages in the experiment phase. So one is just getting the data. This is very, very simple. It just runs a query that just gets some data back, puts it into a data frame, and then does something with it, right? Hopefully, and this is what I'll show you, you will see the benefit of doing this in a dataset version, right? Instead of just downloading it or like pushing it to a CSV file somewhere with some random name and then using that random name in your next script. But then if you change the data again, it will have a different name and you'll overwrite stuff and things like that is why these dataset versions, but also the experiment manager exists, right? So like I said, you have dataset versions that will be passed through from script to script, right? So the getData.py will get the data, put it into a data set, then the preprocessed data will get that data set instead of just a random CSV file on a disk, and then process the data, obviously, or pre-process the data, put it into the preprocessed asteroid data set long term, and then we have a new data set that we can then use to actually train the model on, right? But this is very, very useful because now we have multiple versions of this data set. It's very easily accessible. And then obviously we'll also be using an experiment manager. So regardless of which kind of experiment manager you're a fan of, having one is very, very useful at the very least. So what we'll end up doing is we'll run these Python files and they'll actually end up in an experiment manager, in like a list that keeps track of every time you run the experiment. So the slide is blurry. You can see the slide on the repo. If the slide is blurry, and I have a feed right here, it doesn't seem to be, oh, slides are fine now? Okay, perfect. Right, so what problems are we solving, right? This is the last slide before I dive into the code. Essentially what I want to do with this is make sure that I'm not preaching to like a non-existing problem, right? So if any of these things fit your workflow, if you have ever had the inconvenience of having this in your own life, then these are the kind of tools that you want you might be interested in. So what problems are we solving? Experimentation is inherently chaotic, right? So once you get like a new project or you start something new, it can get really chaotic really quickly. And every single time I tell myself I want to be better organized or I want to do things better and like have better folder names and better file names, it never ends up being just what I want. And so this is what an experiment manager tries to help with. Experiments are also hard to reproduce. And this is something that is not necessarily part of every experiment manager. But what is very important is that you're, especially in, for example, like academia, but also if you're in the company world, right? It's very hard to reproduce your data, to reproduce your experiments, sorry. So you're constantly changing stuff, you're constantly adding or removing hyperparameters, and it gets really messy really quickly. And also, it's not necessary that Git can do everything for you here, because there's a really big change. Software development, you do something, you test it, it works, you put it in Git and as a commit, and it's there. But in data science, you actually don't know if the model is performing good, even if it works. So you won't end up committing every single parameter change that you do, which makes sense. So that's also something that an experiment, which is a single run of your code, should be able to help with. And then it's difficult to compare and share experiments, right? So if you just dump everything to disk or put like a zip file, I had a colleague actually once that at the end of his notebook actually just had a function that zipped everything in the folder, gave it a name and timestamp, and then just put it in a folder somewhere. Essentially, that's how it works. That's how an experiment manager works, only there's a lot more time put into that in comparison. And then keeping track of dataset versions is hard. So now we're into the dataset versions. So if you have multiple versions, you might have multiple folders, for example, but then every data is duplicated, which is already a big annoyance. But also, yeah, you have to keep track of all the different versions. And if your code changes over time, who knows which code corresponded to which dataset version, right? So if you're just putting everything on this, that actually doesn't start or actually isn't very scalable. Again, something that we want to change or like help with. There are tools out there that can help with. And then a last one is sharing datasets to other people or machines is annoying. So if you've ever put a zip file of a dataset on Google Drive, I have. A lot of people actually still do. Sometimes it's warranted, I guess, but in a lot of cases, it just makes sense to have a dataset manager, a dataset version manager that just allows you to pull by specifying an ID, specifying a name, or saying latest, which actually can make life a lot easier. Right, so it's demo time. Enough talk for now about slides, of course. So if I go into my VS Code here, what you'll see is essentially, let me zoom in. I hope you can see it. Please let me know in the chat if you can't see it. Right, so what we essentially have is a few files here, right? So the getData.py is what you saw before, right? And let me just put it on here. The getData.py is here. Then we have the preprocessing data as well, and the model training.py as well. So I'm going to go through these a little bit more into detail. So essentially what the data set or the getData.py will do for you is it will just get the data, right? But to get the experiment manager working and just to add all of the tracking you will ever need, you actually just have to add a few lines, right? So we'll start by going over the experiment manager. So essentially we're using ClearML here, obviously. But we're going to import a task and we're just going to initialize it. And this is essentially all you have to do at first. If you want more details, obviously you can add more. But this is actually the very, very least you can do. If you just want to experiment around and just add a lot of things, you can just add these 2 lines and it will already start tracking everything for you. You just can give it a project name, which is in this case global. You can give it a task name. In this case, it will be get data, and it will correspond to this entry in the experiment manager, right? Then task type and reuse task ID are 2 other non-important arguments for now. And now comes actually the meat of the code. In this case, it's really not a lot, right? It's get data.py. So essentially, what is already good practice is if you're doing experimentation and you're doing any kind of parameter or using any kind of parameter, it actually makes a lot of sense to put it into a dictionary already. Like one global dictionary or like a configuration file, if you use Hydra, for example, this actually makes a lot more sense because it's easier for you in general, regardless of you using an experiment manager or not, right? But what is and the added benefit of that is that you can just call task.connect this config, and then the task itself, so the ClearML experiment, will now be capturing this as well. So we know that these are parameters, and that will become very, very important later. We can actually change these and then clone a run, and it will be injected into this configuration dict. So that's really, really useful. Then we just get some data, right? So the only thing that we did so far is just initialize the experiment manager and connect our parameters. And then the next thing we're going to do is get the data and the path to the file, right? So this is essentially the only line that is of actual code here. And it's just essentially saying, like, I want the database, I want to query the database to the DF, and I want the query to be this, right? So the global dictionary query. And then it'll say dataset is downloaded too, and it'll print ahead. So let me run this for now, and then we'll come back to it once it's done. And then what we'll do, so like I said before, it will already have captured now. Okay, we essentially what we did with this run is we got the data from a query and we saved the query. That's essentially what we did here. And then we want to create a ClearML dataset from it. Like I said before, the versioning is really, really useful. The fact that you can just get the dataset with its ID or with its name is super useful and a lot more easy than just putting it on Google Drive, right? And it's also very easy to just make one, right? So the only thing you have to do is import the dataset object. You create one, give it a name, give it a project, which will probably be the same project as we saw before, and then add some files. Right? That's all there is to it. So what this function did, it essentially just created a data frame and also a path to the data. And then the path to the data can just be added as files to the data set, and the data set will just gobble all the files in that path and put them in a version. Now, there is one more thing that a dataset versioning tool can do for you that is very handy to start using, and that is very much better than putting it on a disk again. And that is actually logging statistics as well. So depending on which version you have in your data set, your statistics will be different, right? If you have, for example, feature distributions or a head of the table in this case, or a lot of different plots that you want to attach to a specific version of your data set so that you can very easily visually verify that the data set you're working with is the one you thought. Does the data set object support unstructured data as well? Very much yes. So if this is like a, what's it called, like a folder full of images or even video or audio, it will work out of the box. So that is definitely no problem. Yeah, so it definitely does support structured text. This was a question on the chat. And then once you've reported all of the things that you wanted to do, for example, if you have images, in this case, you could say have a class distribution, right? So just a histogram with all the different classes that are in your data set. And then you can finalize it, which essentially just auto-uploads it, right? So then you have your first version. And if you run this, you'll get a created dataset ID. So if I look at the output here, I essentially run it. It says I created a new task with this ID. This is the page where you'll find all of the information there. I just found the simple CSV file called nasa.csv, which is such a cool name. And then you also have the data frame as well, like the data frame head that we just printed a little bit before here. Oh, I had it, And then we created the dataset version and uploaded the different files. How does the dataset versioning of ClearML compare with Metaflow? Actually, to be honest, I haven't used Metaflow all that much, so I couldn't tell you. And but it's a very interesting question. And if you go to our Slack channel and ask it there will definitely be people that can answer this in more detail. So what we'll end up with, if I go back to the slides. But now we can go into the projects here, and you will have an MLOps World. So actually, I'm going a little bit too fast here. Essentially, you have an overview of projects. This is the experiment tracker. Let me zoom in a little bit. This is the experiment tracker. That should be good. This is the experiment tracker, and you will have your different projects, right? So if you're working on a lot of different things at the same time, it's very, very easy to just have an overview here. And this is essentially what I meant for myself when I said I'm going to try and keep an overview this time. This is usually how it works. Like, it actually does work. You just dump everything from a single project in a single file. So what do we have here? We have the get data that I told you before, and we also have the raw asteroid dataset, which again is a really cool name. So if you look at the get data, it saves everything. And that's the main point of an experiment manager. It saves everything without you having to do very much. So in this case, it saved which repository it is on, saved the branch, it saved the get data. But also, if you're, like I said, not committing everything, uncommitted changes as well. And all of these uncommitted changes will allow you to, at a later date, completely reproduce this experiment from scratch, because you can just clone the repository, check out the branch, and apply all of the uncommitted changes that weren't part of your Git. Also, it will auto-detect all installed packages, so you don't actually have to make sure that your requirements file is up to date, but you should. But this will actually detect it from the environment instead, so you don't have to. And then there is other information that is interesting at a later moment. Then configuration. Remember, we connected our configuration dict here to the task. So essentially what we have here is a separate section in the experiment manager where we can have these hyperparameters, they're called. And this will become very, very handy, but also just in terms of, for example, comparing different experiments, this will also be very handy. But like I said before, it will also be very handy for really cool automation that will come later. There are no artifacts. These are like model files or other big files. Obviously, there are none in this case. It's just a data set, but that's a separate entity. Info, just like when and how it was run and on which machine. Also console output. So every single thing you print is never lost. And this is already like a very big thing that will save you a lot of time if you can input it in your workflow. Scalars, plots, and debug samples, we'll see that in the model training, because that's usually what they're most interested in. Right, so the raw Astro dataset is our dataset version, and we see that we have our dataset content, which is nasa.csv. Like the person that asked the question, if here are your images files or your video files or whatever kind of unstructured data you want, those will all be listed here as well. In this case, it's just a single CSV file because we're doing a structured data demo. The artifacts themselves is the data itself, which you can download as a zip, and this will actually be a diff, right? So we won't save everything each time. We will build on top of previous dataset versions, so nothing is duplicated, which actually saves your disk and your wallet big time. And then we have some info again, console output, and in the plots, actually what you see is here is the reported plot that I did. So if you actually add report table, in this case, you could do report plot or whatever you want. You have the head of the table. You could also add some images, some preview images or stuff like this. Those will be in debug samples. And then you have a nice overview of what is in your data set. The genealogy will become important later, but for now, it's just a single point. There is no data set that depends on this one yet. Talking of which, let's go to the pre-processed data, right? So this is the second stage. I'll start to go a little bit faster from now. So task init, we already know this. We initialize the task as pre-processed data. We create the folder that we want to put the output, the pre-processed data into, if it doesn't already exist. And here comes a little bit of the magic of the dataset, right? The dataset version. Here, you would have to specify a specific path to your actual CSV file from the previous step, but you don't have to do this now. And this also means it's very robust to change of where it's running. If it's running on a remote machine, this will still work. If it's running from a different folder, this will still work. So essentially what this does is it gets the dataset name, in this case, the latest of the default, the latest version of the dataset with that name. It will get from this project, and it will essentially return a local folder. It will download it for you using caching. So if you run it again and again and again, it will just use the same thing that it already downloaded. get a local copy will give you a local folder. So we're saying here we're using that data set. Then we're doing a little bit of pre-processing. It's not much. So in this case, we're just reading it as a data frame. We're creating a new feature called average diameter, which is the average, surprise, surprise, of the diameter in kilometers and the diameter in kilometers maximum, like the minimum and maximum. And then we essentially do a subset of all of the data. So there are a bunch of features that we're not interested in, so we subset it. And then we save it to an x.csv file and a y.csv file, right? And so if you're a machine learning engineer, this is very, very well known. This is essentially your features and the thing you're trying to predict, which is, in this case, the column hazardous, yes or no. So you've put that out to a CSV. You've printed the y hat so that we have a little bit of visibility. So let me run that for now, that we can see it later. Right, and then again, we're going to create a new dataset version. So in this case, what we actually want is we want to be able to always go back if something goes wrong. If our model doesn't do what we want it to do, we can always go back and then take a look at this dataset version and see, okay, what actually was the original data and what was the x and the y data that we added to it. So instead of creating a whole new dataset for x and y, what we end up doing is adding the x and the y to the original NASA, and we can always go back. And so how you do this is just create a dataset just like you would normally, given the project, just like you would normally, which is in this case the same project as the dataset that we had before. The dataset name will simply be preprocessed asteroid dataset, which speaks for itself. But now what we can do is we can say, okay, I want parents dataset to be a list of this dataset. And this dataset is the one that we just pulled before. So it's the raw dataset. And because you say this is the parent, what will happen is if we put the x and the y CSV files in this new dataset, we'll also still have a link to the original data in the original dataset, which is the nasa.csv file that we used to train on, that we used as raw data, right? So you can always trace everything back. And then again, here you can add some tables and you can auto-upload it. So if everything went correct, then you see here, we created a new task again, we created a new dataset ID with the data frame with the y, so the x and the y, which is what we'll need for training in just a minute. And then we uploaded it and it gave us a dataset ID. And if we go to our experiment manager, we can very clearly see here we have the pre-processed data task, right? It got tracked just like everything else. And then we also have the dataset version. And if you go to plots here, what we'll see is now this is not a point anymore, a single point. It goes from this to this, essentially saying this is like based on the previous one. This is the parent from the previous one. And it's actually very useful to see in the dataset summary as well that you have the raw asteroid dataset, which was there before. We added one file, the nasa.csv file, the size as well. And then we have the preprocessed asteroid dataset, which added 2 files additionally. And then if we go to the configuration, we see the dataset content that now everything is there. So we can always go back and see what happened. Right. And then finally, for the model training, and this is where it gets interesting, again, we do a task.init, nothing special. We do output URI true, which essentially means if you encounter a model somewhere, also upload it. Also keep track of it, right? We'll use this later. Essentially, this is saying if you ever run this remotely, run this in this Docker file for me. I don't have to do anything else. And then in very much the same way, we just make some a global dict with some training arguments that we can then use in the rest of our code, right? This, again, is very good practice in general, even if you're not using an experiment manager. Then we connect it to the task, so it gets logged. And then we again get the latest version of the dataset, but this time the pre-processed dataset. We get the local path, and then in the local path, we get the x and the y from there. So now we have an x and a y in the data frame. We get the x train and x test, y train and y test, as every single machine learning engineer ever has already done. And then we create the D matrices to train an XGBoost model on. We actually train the XGBoost model, and in this case, we actually don't have to do anything but save the model. So essentially, we want to save the best model that the XGBoost trainer finds for us, and then we want to plot some of the data some of the feature importances, show the plot, and then do accuracy and recall predictions on that, so calculations, sorry, on that, and then log those to the task as well separately. Now, bear in mind, we didn't actually change anything or added any line of code specific to ClearML but you will see that still the XGBoost model will still be logged, and the performance plot will still be logged. And that's because things like XGBoost, PyTorch, TensorFlow, stuff like that, and Matplotlib will always be automatically connected to ClearML. So you don't even have to add a single line, which is really, really cool. So if we run this, I was too late with this, so this will take a little while. But if we run this, what it'll essentially do is just do the normal code, but then it will hook into the back with what they call AutoMagic, which is my colleagues. They call it AutoMagic, which essentially just takes detects that, okay, you're using that library. I already know how that library works, so I know exactly where to find the model, even if you don't tell me to. Which, again, you can always disable it if you want to, but by default, this saved my ass a lot of times, mainly because I forgot about it or whatever, and then it's there, right? So as you can see, this is the plot.show, right? So you get the different feature importances. The default view of Matplotlib is not ideal. It cuts off the names, but in ClearML it will actually be visible because, we saved it there. So right now, it essentially said, okay, we have a model with accuracy 9925 and recall 1, which is really, really good. And it uploaded the model to this place, which is already really interesting because now we have a model, right? If I go back here, you'll see that the model training, we have all our variables here. We have the artifact, which is the actual model here. If I click on it, what we can see is this is the actual model URL. So it's actually saved. Excuse me. It's actually saved. We see that the original experiment that created it is model training. We can click on it and go back there. We actually have the ID as well. If this was a deep learning model, we could add the network layers here. If there were any labels or metadata, we could add that here as well. So this actually is a very, very easy overview. Like this, it was just adding a few lines, but now we have everything in a nice list, right? And what is really interesting right now is, remember that I said that it was very important to put everything in the hyperparameter, so like to connect the task essentially to the hyperparameters. So if I go back, you see here training arguments, all the different things, and then we connected it to the task. So the task not only knows it from the code, but also now knows that these specific variables are very important. And what we can do here is we can essentially say, okay, this is not good enough. I want a clone of this model training, right? And then I want to, because it's now in clone, it's in draft mode, I can edit all of these variables. Now, all of these variables are defined in code. So this is weird, right? I can just change them from the UI. So essentially, you can. I can change that, for example, to 420, which is a difference. And then what I can do is I can say enqueue. I can enqueue it into a queue. I have several here set up, but I'll enqueue it in the default queue. And right now we have no workers assigned. We'll change that in a little moment. But what that essentially will do is it will enqueue and take all of the different, let me maybe first start the agent so that I can start working. So what I have here is very simple. It's just in a specific terminal, in a different terminal. You can just run on any machine that you need. It could be the faculty machine with the huge GPUs. It could be this machine. It could be your laptop, whatever. ClearML daemon, queue, default, and services. Services will come later for the pipelines, foreground, and then the Docker file. And if I run this, I'll run this on all four. So we have four of the agents here. And what will end up happening is these four agents will now sync as workers to the to the experiment manager, right? So from now on, we can run anything remotely. And the really interesting thing is, remember that I said that we tracked everything, including the Docker file, including the installed packages, including the differences like the git diff. This means that you can essentially reproduce your experiments anywhere, also on these remote machines. And that's actually the whole power of this, because if I now go back, you can see that it is in fact running. It's not pending anymore because one of the agents took it up, is now recreating the environment completely and is rerunning it, but it is injecting this new parameter that we made. And that's really, really cool because now I can just clone my code from the start and just change a bunch of parameters. And if I made my code wide enough and robust enough that it can just do everything based on parameters, I can change them all. And I can change them with almost no effort and run them on a remote machine as well. I should mention that this is not even necessary if, for example, you use Hydra or argparse, Python argparse, or any of the like major argument libraries, because then again, just like the XGBoost and the matplotlib, ClearML will already just grab that, and you won't even have to connect the arguments, but it will have the same effect. You can change everything here. Of course, you can live follow along with the console, right? So it just trained a new model here, and a process completed successfully. We see the scalars here as well. Oh yeah, I didn't actually go over this. So you have scalars and plots, and scalars are essentially output metrics, right? So in this case, automatically, I didn't do anything else. The test and the train accuracy over the multiple iterations of the XGBoost model are reported automatically. And what is very interesting now, and this is one of these powerful features that you start to get once you're actually using them, is we can just select these two, which is the clone and the normal, and then we can compare them. And we can easily compare it. We can see, okay, they were obviously run at a different date, so that's not a huge deal. But also we can see the parameter. And everything that is read is different. So like I said here, this was the original task with 42 as a seed. This is now 420 with the new seed, right? And this makes it very, very powerful, because you can also then compare the scalars. So in this case, for the accuracy, we see that the model training of the normal model training was 9925, and then the clone that we give 420 is just 99. So it lost a little bit of performance, but it gained a little bit of recall. It also lost a little bit of recall. So in this case, you can very quickly compare the two. You can give them different colors. You can do whatever you want. So this actually makes it very, very nice if you have multiple hundreds of different experiments and you want to easily compare. It also automatically monitors your GPU, your CPU, your disk usage, stuff like this. So this should normally be a line, but it was very short. So that's why you can't see it. And remember that we also plotted the feature importances. We can also compare those, right? So now it's very easy or very handy to see the different features and all of the different matplotlib plots that your code might produce just side by side, which is very, very useful. Right, so now we have our workers here and we have our queues. So we can go one step further, and that allows me to go back into how does it manage GPU? So I get a question here, how does it manage GPU? So I assume that you manage, you mean the agent, right? So if you're starting up an agent like I did here, essentially it is it's just using Docker in the backend. So as long as your Docker, you can give all of the Docker parameters that you need all the way in the CLI. So if you can just send the GPU Docker flag, which you can, to the agent will be able to run the Dockers just on the GPU. And in this way, it can schedule it. There is dynamic GPU scheduling. Oh, that's a thumbs up, so it was right. There is dynamic GPU scheduling. You can find the docs. That's a little bit too far for this. But you can also run these agents as a Kubernetes pods. So it's really, really powerful in what you can do there in terms of GPU sharing and stuff like that. Right. So let's get back one moment to our graph here. So wait one moment. So a recap. What we saw just now is why you should use an experiment manager and always use an experiment manager. If you just add those two lines, that's already perfect, right? That's already very nice. It can get better if you do data versioning. Again, I'm not saying you should use ClearML at all. Like DVC is a very nice data versioning tool. ClearML has its benefits. There are others out there. I'm essentially just saying, please use those tools because, yeah, we see that they're not used at all sometimes, and that's really, really bad. Cloning and editing experiments is a very powerful feature. So at the moment you have your experiments, it's completely reproducible. You can start doing everything you want, anything you want. And then we also saw the agent for remote execution. Right. Take a breath. So we went through the experiment phase like that. This is actually a part that a lot of people already know and already use, right? Now comes the productionizing phase. So essentially what I want to do here, or I want to show you, is how easy it can be to just build on top of the effort and the blood, sweat, and tears that you put in to add these experiment managers and experiment manager calls. And I want to show you how powerful they can be once you start scaling up. That's the idea. So once you're in the productionizing phase, what we're going to do is we're going to take a look at pipeline.py, which will essentially is a small script that can chain together these experiments that you just wrote and then build them into a pipeline. And remember, we can clone those experiments. So we can just clone every experiment, build a pipeline out of it, overwrite the hyperparameters, and then come out with a wholly different thing. So that's really, really fun. Let's start with that. And obviously, we'll be running it on the agent because now we know how to do it. We'll get the data first, we'll pre-process it, and then we'll make 3 clones of our model training script, our model training experiment that we saw before, and then inject the different parameters in that. So to do a sort of light hyperparameter optimization, and then have just a simple function there that picks the best model and tags it. But again, what are we solving here before we dive into this? So remote execution is time consuming to set up. With this, I mean that especially if you're with multiple people, if you have one or more very powerful machines, either like in your faculty or on the premises of the of your company or in the cloud, it's really annoying to have to set everything up with SSH, or then it takes a little bit of time to put everything like an Ansible script or automate everything. So remote execution can be time consuming, and it's not always ideal. Sharing machines with multiple people suck. I've heard horror stories of like faculty members not having like queuing or stuff like this. So everyone just SSH'd into the machine and just killed each other's scripts, training scripts, just to start running their own because they had deadlines. Stuff like this, we don't want this. There are better tools out there that do this for you. Running a bunch of scripts sequentially is inefficient. So if you have to do it manually, it's annoying. If you have to do it automatically, you have to write the script for it, which is fine, but then you have to update it every single time that it changes, and you can't really change a lot about it. It's inefficient. It's not bad, but it's inefficient. And then rerunning everything with new parameters is even more so, because now I want to start doing new stuff, and I can't do so because I have to change all the parameters. What was the different versions of my code? It's all a big mess. And then again, also monitoring who did what, when, and for how long. If you're just SSHing into a machine, you won't have this, or at least not out of the box. Right, again, demo time. So let me go there to the pipeline.py. Essentially, what we're doing here is we're just defining what's called a pipeline controller. Right? So we're importing this from ClearML automation. I'll go over the functions shortly, but essentially we're creating a pipe here, which is called Asteroid Pipeline. Really cool. In the global project here, and version 001. And it's just creating a pipeline controller is just an object into which you can change stuff and add steps, right? So, for example, you can set the default execution queue to default. Like I said before, the agents that we just started, they're listening to the default queue, so that's fine. The default is fine. The pipeline controller itself will be queued in a special queue called services. And that's also why I made my ClearML agents also listen to the services queue. That's just the orchestrator. That will do all of the bookkeeping, essentially. It's really nice to have it in a separate queue like services, because then later, for example, if you have an autoscaler, ClearML also has an autoscaler, you can actually have it autoscale only very simple machines, very small machines for the bookkeeping stuff, and then have like GPU machines for the heavy stuff. So that's why it's interesting. And then I want to add pipeline-wide parameters. And that's also something you can do, is because we'll see in just a moment, you can clone a pipeline just as you can clone an experiment. So that's actually why you want to add parameters here to your whole pipeline that are then used in subsequent steps. So in this case, I'm making 3 training seeds, and I'm also repeating this query that you saw before in the getData.py. And now we're ready to start adding steps, right? So the pipe add step, the name that we used before is getData, right? So this is an experiment that's already in the experiment manager. You can do it without it being already an experiment manager, but in this case, it's already there. So why not use it? This is the project that we're going to use. The base task name is getData, which is the actual name of the experiment, not this. This was a mistake of me. This is going to be the name of the step in the pipeline. And then what you can do here is a parameter override. And that's exactly what I did manually just a few moments ago, is you can just get the general query. If I go to the experiment manager here, MLOps World, there we go. And I get my data. You can see here in the section general query, this is what we want to override. And we want to override it with the pipeline parameter for query, right? So in this case, it won't change anything, but like I said before, you will be able to change this later on. I'll actually run it already because this takes quite a bit of time, because it has to set up the environments for every step, obviously, to make it completely reproducible. Then we add another pipeline, another step in the pipeline. So this time we call it pre-processing data. And this time we can say, okay, the parents are get data. So this will follow up on the other step. The global config project name, the pre-processed data is the name of the base task, so the actual experiment that we want to use. And this is just as an example, you can, if you want, use pre and post execution callback functions. So these functions will be called before and after the node gets run, and you can change some things here or get some information here. We'll just print some of the information here, but you can add anything you want. And then we have the training nodes here. And then for every training seed, remember we had 3, for every training seed, we're going to create and add a new step that is on the same level, so that we essentially get the data, pre-process the data, have 3 models trained with different parameters, because we can, again, override these parameters. So the random states will be overwritten 3 times to create 3 different model training runs. And then the last one is to select the best model. So out of those 3, we now want to ingest them in again and get the best model there. To be able to do that isn't a big task. So what was interesting is to add a function step instead. And this essentially packages a single Python function as if it was a task for you, but you don't actually have to put it in the experiment manager yourself, which makes sense in case of this smaller thing. So this is the actual function that we'll be using, which is this one. It will essentially just import the output model, so it can report the model, keep track of the current best, and then for each of the nodes that it gets in, it will essentially get the accuracy, see if it's best or not, and then output the best model so that it becomes the output of the whole pipeline. Right, so, as inputs, of course, what we're going to do is for every node in the training nodes, so every one of these 3 nodes, we're going to give the ID as a parameter to the function, but that's relatively easy. It could also be a task, and then it would be a parameter override. Right. So if I start this task, it should have already said here terminating local execution process. And then what this means is it packaged everything, it found everything, and now it sent it all the way through the queues so that for the agents to handle off. Right. In this case, it's still my PC, so my PC is still doing the same thing, but in real life, it could be a completely different machine that is now currently queuing it. If I go into the pipelines view here, you'll see it right here. So asteroid pipeline, this is where we're at right now. So this is what you hopefully expected. You have the get data, the pre-processed data, model training 1, model training 2, and model training 0, which are the 3 trainings, and then select the best model. We have the pipeline parameters. Sorry, if I don't select a single node, we have the pipeline parameters here. So you have select star from df where year is smaller than 2021. And we have 42, 420, and 500 as training seeds. And then we can see here that they're overwritten. We can follow along with the execution of the actual pipeline, or if we select a single node, we can follow along with the progress of a single node, right? So this one is just finished. This one will get going. The 1 minute 40 is a fixed cost. You have to set up the whole environment, install all the packages. Of course, this is the first time it's run in this particular configuration, so it is not cached yet. It is obviously cached over time, but this can take a while, and it's just a fixed cost. If your training takes like 10 hours, this will just be negligible. Right, so hopefully you've been able to see the power of these pipelines. I will now go back to another pipeline. Let me go to this. This is where I actually run this before in a different environment. And what I can actually do, which is very interesting, actually, I won't do that yet. I'll first show you the serving because it's going to be interesting to see how we can actually solve an issue. So I'll leave this pipeline running, get to the serving, and then we'll come back to this pipeline to actually create a new one if it's interesting. Right. So just to recap, what we have seen, we have seen the pipeline controller script, right? How you can just very easily add steps to a pipeline that already exists, and it will just take that environment, recreate it, and rerun your experiments. And then we can clone and change the arguments. We'll see that in just a little bit. But essentially, you can clone a pipeline like you can clone a task, and that's actually really, really powerful. I will see why in a minute. And then also model tagging and querying. So what I mean with that is that if I go here to the different pipeline that I wanted to show you, if I can go to the tag best model and see the full details, which will bring me to the actual task overview, what I can see here is this is the model that it produced. If I go here, you can see that it it doesn't have a tag. It should have a tag. Demos always don't want to work with me. So essentially, this is the one that has the tag. It also is made by select best model, but essentially it gets tagged in this way. And what makes that interesting for the serving later, but also in general, is that you can filter both in the UI and, for example, here I can say tags pipeline winner, so it only gives me this, right? But I can do the exact same thing with the serving, just to make sure that I always serve the model exactly like the one that I want to serve, right? So that makes it very, very useful. So you can do all kinds of fancy stuff with the tagging as well. Right, so model tagging and querying. Now the deployment phase. So this is the last phase. This is in my opinion, most fun one or the most interesting one. Wait, I have a question. So from an MLOps perspective, how are pipelines better than stacking all the steps methods in a script and have experiment tracking with that? So that's a very good question. It is, in essence, it's just easier, right? It is a script that you write, so it isn't very much different. But what is the very powerful difference here is that in this case, like I showed you before, is you can actually override these parameters. So you could technically do that in a script as well. That is true. But the pipeline itself also has the different logs all in a nice environment. So you can click on the different nodes and then see how they're doing. Essentially, you could do the same thing in a list, right? If you just have a script and have everything in the experiment manager, you will have a list of the different nodes running at that time. It would work, right? It's just a convenience thing, I would say. The overriding and the cloning of a whole pipeline is something else, though. Because at that moment, and I haven't shown you this yet, I will show you this part of the deployment phase. But essentially, you can clone a whole pipeline, which means you can then change the parameters and rerun the pipeline just from the UI, right? And that is less easy to do with the script. But again, if you're good at scripting, go at it. Like if you have an experiment manager and everything is tracked, that's the most important part. I think a pipeline is just a convenience and has some benefits indeed as well. But yeah, I hope that answers your question. So got it, thanks. So I hope that was a good answer. All right, so the deployment phase, we're already 52 minutes in, so I'm very glad you're still sticking around. I hope you find it interesting. The deployment phase is as follows, right? So we're going to use ClearML serving, which is a primarily CLI-based tool, right? It's made for convenience so that you can very quickly serve a model, any model, also GPU models. I'll show you the structured data, of course, but there are also examples in the repository for GPU models, just with like a few commands, right? So that's exactly what we're going to do. Also, what we can do here is not maybe to go into that a little bit more. We have the CPU and the GPU workloads. The CPU workloads will be run on Intel's One API, which I think was OpenVINO just a while ago. It is not yet in ClearML as of speaking of this. I mean, it's in the beta, but it will be there very, very soon. The GPU is actually built on NVIDIA Triton, and I think I'm speaking the truth if I say that NVIDIA Triton is really freaking fast. And I think most people tend to use this lately because it supports so many different models. It's so well optimized for NVIDIA hardware that it's kind of sad to not use it. But then there is a wrapper around that does custom pre-processing, custom pre and post-processing, actually. So what we can have, and this is a Python file that we'll look at in a moment, is a pre-processing serving.py that essentially takes in new data, can pre-process it however you want in Python code, sends it to either One API or Triton, then gets the result back, post-processes that, and then sends that back to the user. And then also, what this wrapper will do is it will generate a whole bunch of statistics that you define yourself. And again, ClearML is open source, completely open source. So that means that we essentially offer the metrics that you just defined as an API, and you can use whatever you want with that. It's in Prometheus. It's all sent through Prometheus. So you can pull that if you want to and put it into your own detection models or drift detection models or whatever, own monitoring stack, or you can use Grafana or something similar to do it yourself. I'll be using Grafana in this case which will do the model monitoring, and then we'll induce some drift as well. Right, so again, this is the final one. What are problems that we are solving? Multi-GPU serving, and against a data scientist, it's a mess. It's really not nice. So performance is the main benefit here, right? So if you have Triton, Intel's One API, those things are really, really optimized and really, really fast when compared to, for example, just doing model predict and wrapping it in a Flask API. It has its merits. You can do it very fast, but a model server has the performance edge, definitely, especially on GPU. Multi-model serving and hot swapping. So something else that your model.predict or with the Flask will not do is multi-model serving. If you only if you like code it yourself, but it's not very easy to have it like in a web server that was never made to do this kind of heavy lifting. And then also hot swapping, which is really useful if your model goes bad or you train a new one and you want to swap it out. It's really nice in these kind of model serving engines. They can just very easily shift over the traffic from one to another without any downtime. I think there's even a talk right now about not having downtime for model serving. So there's definitely options out there. Multi-GPU allocation and scheduling, especially also like single GPU, just maximal utilization. It's not very easy to do on your own. So that is also something these things can help with. And then model monitoring as well. So like I said, we will be creating model metrics so we can do any type of monitoring that we want. Right, so demo time again. Right, so let me first go to preprocess serving. So this is again in the same folder. And this is a kind of object that we have to overwrite, right? So it's just a class preprocess that we get or that we create. And it has to have a preprocess or a postprocess function. And the preprocess function will take in the body, the state, the custom collected statistics function. So what this means is that you can have a complete custom Python function that creates model monitoring metrics for you, right? So that you can definitely do. There is a state in which you can store things that will then get back out or like put back out again in the post-processing after the model was sent to the model server. Then there is the body as well, and the body is actually what you'll get in, right? And so in this case, what we want to do is, again, same thing that we did before. Good practice would be that we have these functions global as an import so that they're always the same no matter what. But in this case, it makes it more verbose that we can show it. So what you get the body, the values of that will give you a df. That will just be a single line because I'll only be sending single lines. And then we do the same average diameter and we do the same subsetting of the different columns, right? And then we create a DB matrix, and that's what we'll actually send through to the model because that is what the model expects as an input. And then as an output, we get, again, the state that we can access that was the same as here. But in this case, we essentially just get the data out, which is the output of the model. And then we get the first result rounded as y, and the actual y raw will be the prediction certainty, right? This is not the rounded version of this. So this is what we'll expect going in and out. But now we have to set it up, right? So there are more detailed instructions in the GitHub, but I've already been talking for an hour, so I'll keep it relatively concise. If I go out here, what you'll see here is a serving instance and a statistics controller. There will be a control plane task here as well once we start adding configurations. But essentially, there will be a third task, and that's the thing about ClearML. In ClearML, everything is a task. So just like we saw, the data set is a task, but also the serving and statistics here are tasks as well. And so what you can see here is the serve instance has it still has an asteroid. Let me just take a look. Okay, so I forgot to remove this from the practice run. But essentially, what we want to do here is we want to set up our endpoint, right? So the first thing we're going to need, and this is actually the powerful step that this whole integrated pipeline can do for you, is the first thing we want is our model file. But our model file is already tracked, right? Because if we go to the MLOps world, we go into the models, these are the models that were created. And actually, we can go even further and we can go into our pipeline. And if everything went well, the pipeline here created a model as well. So if I go to the select best model, what I can do here is find the model ID that I created. We can also go into full details of the last step. And then under artifacts, this will be the model as well. So if I click on the model here, we'll have the pipeline winner. So this time it is tagged. And we have the ID here as well. So what we want to do now is use ClearML serving. I told you that it's a CLI tool, right? So, and we want to add the model add. So these are just the history of the things that I did. This is essentially what we want to do. So let me change the ID. So we do ClearML serving. I hope this is visible. If it's not, let me know in the comments. ClearML serving, we give it the ID of our, this is what is included in the more detailed instructions in the repository. Essentially what you'll do is you'll create a, let's say, control plane task. And this is where you push all of your changes to. This will handle everything that you want. And you essentially only need to know the ID. So this is the ID of the one that I want to use. Model add and then engine XGBoost. So this could be XGBoost, sklearn, I think Triton. So in that case, it would be GPU based, and any of the big ones like PyTorch and TensorFlow are supported there. We want to create an endpoint called Asteroid, and we want to preprocess it using the preprocessing serving.py that I just showed you. Then we want a model ID, or want to give it a model ID, and we essentially just give it the model ID that we just created in our pipeline, right? If I add this, it will sync all the changes. And now, if I'm not mistaken, let me go back here to DevOps. Now we have 3 tasks. So now the serving control plane is back up and running again because it can go to sleep, but it doesn't matter because this is essentially our configuration endpoint. These 2 are actually doing the heavy lifting. Excuse me. So what we see here is that we just created an endpoint called Asteroid with the model ID that we saw here. We have no metrics yet, we have no canary deployment, and we have no model monitoring yet. The statistics controller is also still empty, but these, if we go to the serve instance, what we can do is we can go to the plots here, and it will give us an overview of all the endpoints that are currently here, along with the ID of the model that is actually served. So in this case, if anything goes wrong or things are not going well or whatever, you can already go to the model ID and figure out exactly, okay, this is the model ID that is currently being served. If I click on this, I will go to the original task that created it. If I go into info here, I can see that its parent is Asteroid Pipeline, and then I can go there and actually find out which was the code that actually generated this model. So this backtracking is really, really powerful. Right. So if we go to our model endpoint here, now we should be able to send some data to it, right? This is all there is to it, right? You had to set up like a Docker Compose, which I didn't talk about because it's like a little bit too complex for this scope. And you have to add an endpoint. And that's the only thing. You have to like get the ID of the serving control plane. And then the next command to do is immediately this one. So this will already give you an endpoint. And if we go to our code here, and now it gets a little bit interesting, we can start to set up a model inference script, right? So what we do here is from ClearML, we get the data set, we get the global config, and then we get the data set just like we did with the preprocessing, right? So we get the raw Asteroid data set. Get it here. Oh, it has to still connect to kernel. Everything has gone to sleep in here. I should have been shorter on the ball. Right. So what it essentially will do now is it will just download that data set and then give you the local path. The actual data path is the nasa.csv file. Right. I'll read the file, and this is just the original data, right? So nothing changed here. What we can do now is send the data, right? Send some requests to our API. So you can see here it's requests.post. Oh, not move this. It's requests.post. Let me show you the output to my local host. So in this case, I am actually running ClearML serving via a Docker Compose setup on my local host. You can Docker Compose set up it on any machine. You can also actually run it on Kubernetes as well. So you could go as far and beyond as you would want to. Then we serve it. We ping the serving endpoint on Asteroid. This is our endpoint that we just created. This is this one, this serving URL called Asteroid. And actually, it works really well. We get only 200s. we get the y and the y raw just in the way that we expected it to be. And the keynight might have seen that I get here the raw asteroid dataset. This is because we actually send it raw data, and it gets pre-processed by the preprocessing serving.py that we added to the endpoint, right? So this actually makes it really, really useful. Now, what I want to do is induce some drift so I can show you how you can actually start to monitor the model as well. And then we can actually very quickly retrain a new model to combat that drift, right? But the first thing we'll have to do is actually add some metrics, right? So if I search for my metrics here, what I saw before, if I go actually to my experiments here, to my experiments here, what I saw while training the model training right here in the plot section, is that absolute magnitude and minimum orbit intersection, these are so cool names, are actually the most important features here, right? So let's just put some metrics or like monitoring on those two features and see if they change over time. So what I want to do here is ClearML serving, get the same ID. This is still the same ID of the control plane. So again, we're pushing everything on this control plane, on the serving control plane. And that will then sync every minute or so to the different serve instances and statistics controllers. This so that you can do easy hot swapping and stuff. Right, so where should I go now? So here, we have the ID here. We add some metrics on the endpoint called asteroid with the variable scalar, absolute magnitude, and then a bunch of buckets. These buckets you can easily generate like with this code. This will be huge. So for example, here I want to cut our minimum orbit intersection in 3 buckets. It will give me these buckets here, and I can just use those in the command line right here. So if I do that, it will now start monitoring what comes in for absolute magnitude, right? And it will start monitoring that and putting it into buckets over time. I want to do the exact same thing, like I said before, metric on the minimum orbit intersection as well, because that was the second most important feature. So it's very valuable to start looking at that as well. So we have our metrics here. If we go to our serving, on the actual serving control plane, you should already be able to see this. So if we go to metric logging, we go to our asteroid endpoint called asteroid. Metrics are absolute magnitude and minimum orbit intersection, right? And every minute this will sync. So if I go to the service instance, it's not yet synced, but it will take a little bit of time. You can always find it out if you go into the console. It will give you that its new configuration was served. So in this case, it was just too late, I think, but it will. Oh, there it is. So now it's synced. No worries. And so everything should now be put into Prometheus in these buckets, right? If new incoming data is seen. So what we can do is we can go to Grafana and get our dashboard set up in such a way that we get from asteroid the minimum orbit intersection bucket and divide it on the minimum orbit intersection sum so that we have like a histogram that is 100 in total, right? So we want the percentage of data in each bucket, essentially. And we want to create from that a heat map over time. So essentially, if you get your heat map, your histogram, and then put it on its side, you have your histogram for one specific point in time. And now you can go over time to get an actual heat map. And that's what we'll see in just a bit. So if I set it up this way, and then I start sending data, we should actually be able to see, let me just send this data again first. Should be able to see incoming new metrics. So I mean, last 5 minutes. It will take a little while, and there we go. So there is data coming in right here with a certain distribution, right? So I'll put that on 5 seconds for now, and we'll go a little bit further because now what I want to do is I want to induce drift, right? Remember that that was the goal here. So what we can do is we can take every important feature from our data and then fit a distribution to it, right? So let's do that first. And what you'll see here is, for example, absolute magnitude will have the black distribution, right? This is the actual data distribution of the that feature. And what we can do is we can fit an actual distribution to that, and then sample from that distribution as new data, new incoming data. And we can send that to the endpoint as a proxy for what is the type of data that you would want to have come in, right? Your model is trained on the black data. So if the blue data comes in, it should be fine, right? But what I'm also doing is for the absolute magnitude and for the minimum orbit intersection, I'm actually multiplying it by 2, right? So that means that this will be shifted big time. This should definitely trigger all sorts of alarms and be very, very visible in Grafana because it's starting to drift. The actual distribution is shifted. So if we draw from that, that's going to be an issue. I'm going to collapse this. And then what you can see then is we have our synthetic data set, which is essentially this. And then we have our synthetic data set with drift. And what you can see is that the mean here is like half of that of the drifted one, right? So what we're going to do is we're going to first send a bunch of normal data here, and then we're going to send a bunch of skewed data as well, right behind it. And hopefully you should be able to see that in Grafana, because then you can start to build some drift detection models on top of that and make it very, very nice and very, very visible. Right, so this is the data that's coming in. We're going to have to wait for this a little bit. So the first thing that I'm going to do is imagine you have a drift model, or you have model drift. The first thing you're going to want to do is trace it all the way back down and see where did it come from, right? What can we change? So if I go here back to our serving instance, and we go into our asteroid model here, what we can do is we can go to the model and go to the original test model and then the original pipeline that created it, right? This is the old UI. So if we go into the new UI, this is actually, we know that this is the pipeline that actually created it. And what you'll see here is that, okay, we have select star from df where year is smaller than 2021. Obviously it's 2022 now, we have new data. Obviously it's going to start in drift. We should now clone, and this is where we finally come into the cloning of the pipelines. We should now clone our pipeline and have new data come in, right? So what I'm going to do is click new run, and it will ask me if I want to override any of my pipeline parameters. And actually I want to have 2022 here and run it. And this will essentially do the exact same thing, but now inject and get data, this new query that will get me new data, right? And this will essentially lead to a whole new model that will then use later on and deploy as a canary endpoint, so that we can start to roll out our new model that is fixed for drift. Right. So if I go back to Grafana, it should still be firing up here. And then after a while, it should start drifting, right? So what I can already do is, because we're still waiting for this, it should start drifting in a little while. What I can already do is if I go into my DevOps, so my actually serving, what I want to do now is actually serve a new model, and the pipeline isn't ready yet, but I have obviously already made this pipeline. And as you can see here, it's actually 2022. So this pipeline is an exact clone. It's essentially the same thing as what I would have if the pipeline was already there. And I can get the model ID from here, right? If I go to full details, I can get my artifacts here, get the best model. There we go. And copy the ID. And what ClearML serving allows you to really quickly do, and this is so cool, is model add. There we go. So this will allow me to essentially create a new endpoint on the same 44A task, right? The control plane. Model XGBoost is all the same. The endpoint will be called different though. Asteroid drift corrected this time. The preprocess is preprocess serving.py. And the model ID is the one that we just copied, right? So if I put that here, run that, what will happen is we'll see the actual endpoint pop up in our experiment view, right? That will be here. And then we go to DevOps and on the control plane. So the endpoint is now here. So we have an asteroid drift corrected endpoint with a completely different model ID. Now, I am still sending all my traffic to the asteroid endpoint, right? So I want some kind of way to first test out this drift corrected model, just so that I'm sure that it works, right? So what I can be doing, actually, let's see if we have our drift already. Not yet. Should have timed this better. Always with a live demo. So it's still, there we go. So it's still sending normal data. Now it's starting to send skewed data as well. If I go here, what I can do is add the canary endpoint. And this is actually very, very easy to do and so useful. Is again, we take the ID of the control plane, we add model canary, an endpoint, we give it a new name. This new name will be asteroid canary. And in this case, if you send requests to asteroid canary, it will be 90% of the time routed to the old asteroid model that still suffers from drift. And then 10% of the time to the asteroid drift corrected model, right? The model that we just added. So if I just add this, you can see with just a bunch of CLI commands, we now have two models completely running on two different endpoints from two different pipelines, from two different pipelines that are constituted of a lot of different experiments, and they're all served on an asteroid canary endpoint. So this is starting to get really interesting for in like real life, right? And this is where you actually see drift starting to happen, right? And so if you use Grafana, you can also add things like alerts, right? So one alert is currently firing because it detected that something went wrong. And if I view it, you can see that, okay, obviously this is the, let's say, temporal difference of the distribution of your metrics over time. And so the distribution is starting to shift big time, obviously. So this is why it's alerting. And then you can get Slack alerts, you can get email alerts, you can get whatever the hell you want in there. If I go back to my dashboard here and go to the last 15 minutes, you can start that it seriously starts to drift over time, and it's very, very visible with these kinds of plots. So it's a very nice way to keep everything like this in check. Excuse me. And then obviously you can add things like latency, things like the drift that you already see, things like output classes. You can all add this yourself because it's Grafana. It's all in Prometheus. You can add it however you want. Right, so we started to send skewed data, but I want to first check if my endpoint is already online, right? So what I can see here is that we actually do have an asteroid canary right now. So if we go into our serve instance, not our control plane, but our actual serve instance, we can go into the plots and we can now see our distribution here. So we have our asteroid, old endpoint ED9. This was the old model that we served before. And then we have the new model that's trained on 2022 data as well. And then we can also see that there is a third endpoint called canary, asteroid canary. So technically, if we send requests just like we did before, but to the asteroid canary endpoints, we actually end up 90% in the asteroid and 10% in the asteroid drift corrected one. And I should, yeah, probably not. This will probably crash if I want to interrupt it because Jupyter is Jupyter. Let me just kill it for a second. But what we can then do is, there we go. That's starting to, yeah, then we still have to import the dataset again. And then we read the CSV file from the dataset. If it's there, there we go. We have the PDF. There we go. And then if I run the same, oh wait, yeah. If I run my output here, yeah, this is difficult to see, obviously, but I'll send the same 0 row here the next time it's running, and then we can easily see that, yeah, it's actually sending to two different endpoints. So let me do that right here. Oh, it's obviously not sending it to the canary yet because I'm still sending it to asteroid. So canary is now the new URL. To make it sure, or to make it clear, if you go into the repository of ClearML serving, you actually have a way to have this kind of endpoint fixed, right? So you can just publish a new model /1/2/3/ whatever version you want, and it will automatically update the canary endpoint for you, so you can always send your people or your users to this single endpoint, and that makes it much easier. So if I now have this, then technically it should start. There we go. So I'll let it go for a minute. But as you can see, about 90% of the time, you'll see 1.0, sorry. And then the other one, you have 0.99, which means that it's a different model. It's a different outputted prediction than the previous one. So about 10% of the time, we see that the requests come back in as a different request. In this case, the rounded version is still the same, but obviously we have like 99.9% accuracy at this point. So it will be only small changes, but there is a different model behind this all. So this was just with a few commands, very easy to deploy. And then we'll go to the look at the eye candy one more time. So this is our model drift that you can see here. The alarms were blaring, so everything can be done there. And you can just rerun your pipeline with a different, it's still running. It's still running. So this is still going, but you can just run your pipeline all the way again. It will select a new model, and you can just immediately deploy that model on a canary endpoint. So that's really, really powerful. Right. Finishing up, we have our recap. So what essentially we did this time, we didn't end up setting up a server, but you can still read in that in the repository and the documentation of ClearML serving. We did define custom pre and post processing, which we can see, right? Or you can do whatever you want in that function. You can even send states through. Also, we served a model from the experiment manager. You don't actually have to have your model in the experiment manager. So again, we're open source. You can use all of the different constituents of ClearML. You don't have to. So if you don't want to, you can just launch the model and have it run on Triton, and it will just ingest it. You don't have to use anything else if you don't want to. But you can actually serve a model from the experiment manager, because your experiment manager is essentially your model repository. If you also use the tags, especially, you can query on the models as well. So if it's your model repository, you can just select, okay, I know that this is the best model because it's trained by this pipeline, click, 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 and it's all there. So serving the model from the experiment manager and then setting up model monitoring using Grafana. There are more detailed instructions in the GitHub repository of this example if you want to try it out for yourself. Right, so closing the loop, we just did the drift detection. So to recap, we created the get data, pre-processed data, and model training. We created 2 different data sets that are connected to those. We created a bunch of different experiments that are tracked in the experiment tracker and that are comparable, that we can compare and that we can share even. I actually didn't show that yet, but it's really easy to just go to, for example, the training, and then right-click, share, and now you have a link that anyone that is on the platform can use. Also, if you don't want to use app.clearml, which is our hosted version, you can still just use the open source server. Again, we are open source, just a Docker Compose, and you have this whole website and backend running on your own system if you want to. And then we have created a pipeline built on from those different experiments, and then we have served that specific model. So that was demo time. I actually already showed it to you, the drift detection. So I think we're through 1 hour and 23 minutes. So I think there's a bit more time for questions. But thank you so much for sitting through this. It's been a while. But yeah, feel free to post your questions in chat if you have any. If you have some feedback, if you want to see something else, or like have some questions still, I'll try to answer them to the best of my ability. If you want to get started, go to clear.ml or app.clear.ml if you want to get into the console straight away. This is the GitHub link to actual ClearML. As I said, it's open source. We have a Slack channel as well. If you ever run into any issues with ClearML in general, or MLOps actually in general, you can go to clearml.slack.com and we will help you out. We have a Twitter, ClearML app. We make the goodest memes, especially LSTMAO, which is a colleague of ours. He makes the bestest memes. And then I'm Victor Sunk. So you can find me on Twitter right there as well. You can try it out for yourself. It's open source, so feel free. I have one question already. If I have a machine with 2 GPUs, I guess we can make 2 agents. Each agent take control of a GPU. ClearML agent will manage the GPU. Does it take care of queuing the tasks and avoid CUDA out of memory? So several things there. So if you have a machine with 2 GPUs, I guess we can make 2 agents and each agent take control of a specific GPU. Yes, exactly. That's something you can do. I am not completely up to date with like the dynamic scheduling that ClearML can do, but yeah, if you have a machine, the easiest way with those 2 GPUs is to have like 2 different ClearML agents, and you can give those ClearML agents the flags that they can only see GPU 1 or GPU 0, right? So then you have 2 different ones. In terms of queuing, yes, you can actually, I'll show you because the pipeline should still be in the queue. Okay, apparently not. Okay, but essentially this is how the queuing system looks like. So you have different queues in which you can see the different workers that use those queues or like work on those queues. You have different experiments that are in those queues, and then you can actually change their priority as well. So if one is spazzing out or like freezing, you can just abort it straight away and it will just send a kill signal. You can say that it should wait or like be, let's say, give its place to a different experiment by just dragging it up in priority. So that's something you can do. And if it has an yeah, if it's a Linux machine, it will just kill the task, but the ClearML agent should recover from that because it just is managing subprocesses. So the Docker container will probably be killed, but not necessarily the agent, which is why it's relatively robust. So in that way, it should avoid and then it will just say that the task failed. It will have all the logs there for you to like do a post-mortem. And then if you're interested, then the agent will just go straight to the next task in the queue. So it should all be relatively seamless. I hope that answered your question. If I missed anything, feel free. Yeah, thanks. Okay, so that is the question answered. All right, so I think if there are no more questions, then this was everything that I have for you today. Again, thank you so much for bearing with me here. Please let me know if you find it interesting or you want to see anything else. ClearML is actually in a booth on MLOps World right now in Toronto. I couldn't go, but my CEO is there. So if you want to say hi to him, let him know that you came from here. He'll love it. All right, I see a bunch of thumbs up in the chat. I see great presentation. Thank you so much for saying that. That really means a lot. So yeah, thank you so much for your attention as well. And I hope to see you soon in the Slack channel or anywhere else.